Hi. The Labka hospital package called LSP from 1908 was an advanced real-time requisition and response IT system for hospitals that used the laboratory system Labka. The several thousand PC clients in the hospital clinical department had a user-friendly Windows interface. In addition to the graphical user interface with several types of department customized analysis table, the requisition system also had a sampling module called PTB, which could print forms with barcode labels for labeling the various sample tubes. The search system could also automatically search across the county, so the data from the various hospitals in the county, each with their own Labka system, were presented as if they came from one large common database. Cumulative responses could also be printed from the LSP. LSP excelled a very short response time. In general, you should note that the hospital requisition response system can be primitive or advanced, that is real-time, flexible. More on this later. The LSP clients communicated directly with the laboratory HP 1000 minicomputer via a so-called front-end computer and the CSI 101 interface unit as shown here. Patient data, that is requisition and analysis results, were stored in Labka work register and the HP 1000 Image 2 network database, which for one Labka system could contain up to 21 million patient analysis results. An example, a single HP 1000 could connect it to 2000 PCs with approximately 5,500 users. In addition to supporting the 2000 PCs, the LSP HP 1000 system also took care of the laboratory production, that is with 20 analysis machines, 64 screen terminals, etc. And it was possible to produce approximately 20,000 analysis results daily for materials in the several thousand test tubes. At the end of this video, I have included a historical, commercial, technical part. You can skip to this chapter, it might be better to understand what the application is all about, to understand why this system was designed the way it was. But first of all, I would like to mention that the demo video we will see in the following videos originate from a DVD that was sent out as an appetizer to several hospitals in '98. Such a video can be seen here. There are 13 videos on the DVD, which was recorded on a running HP 1000 Labka system in '98. They show some of the many functions in the LSP, but with Danish speeds. Therefore, I have selected only 4 videos, 2 about search and 2 about requisition, and here I have partly translated the audio into English via automatic means. In the LSP introduction video from the '98, I have kept this first image but replaced the Danish sound with this introduction. But first, let us look at the 3 main functions in the LSP. Requisition, sampling with PTBs, and the search function. First, in the IT system, you have to make a requisition. Then you have to make a PTB with barcode labels. It has to be printed. Next, you could search for the result produced via the Labka system, such as the time course. But first, let us look at the PTB, because it's an important module in the LSP, different from many other types of ordering systems. The PTB modules prints on basic of requisition information, sample collection form, PTBs with barcode labels, which has to be put on the respective sample tubes when the sample is taken. The PTB contains additional information from the requisition as well as a few extra reserved barcode labels. When generating the PTB, many different varying conditions had to be taken into account, such as analysis groups, type of test tubes, the laboratory instrument park, configuration, etc. The advantage of printing a PTB for the sampling in question is that they can guide the sampler, and it contains the barcode labels that must be used for the respective sample tube, not a lot of other information. Next, we will look at the search. Of course, we can also look at the communication here from the PC client to the Labka HP1000 system. So now let us go and look at the search process. Searches could be made with a very short search time against all the laboratory, that is against all the Labka HP1000 system in the county, as the request from one client was forwarded to the other LSP front-end computers in the county. Searches was thus carried out in parallel, and the information was collected and then presented on the client as if the search has been carried out on only one database. Here you see an image after such a search. A search demo video, which will come later, you can also see that they have search group adapted to the department most frequently needs. You can also experience the ultra short response time. How this could be so short response time you can see in the last section of this video. Here a short break, only half a minute, because I want to draw your attention to the fact that perhaps later you can see more about the technical conditions and Labka. In that case, search on YouTube HP1000A990. That's a playlist. And if you want to read more about the lab system Labka in your own language, follow the guidelines shown below. Hi. A bit about requisitioning, first in general and then in LSP. The requisitioning process in a laboratory system via external system can have very different designs. The most primitive form can be, for example, creating the requisition information in the hospital information system and then sending it to the laboratory and waiting for accepting return responses, but only for the analyzers you have been ordered. Why primitive? Yeah, that is because the condition around the patient changes. It is in principle difficult to correct information that has been handed over to another IT system when the condition changes. It is often complicated, especially if accounting issues are involved. And there are continuous changes, not only in the intensive care unit in a hospital. For example, it may be difficult to change the requisition after dispatch, perhaps because the PTB has been printed, sampling may be underway, or analysis may be in progress. Some of the responses have been returned or printed, and other additional analyses have been carried out on the material, etc. Conditions which must be taken into account. We had emphasized that the system should be flexible. That is, it should be possible to make changes if the conditions surrounding the patient changes, even if this happens relatively late in the patient treatment process. So let us look at the requisition. Here you see the entry picture to the requisition part. I will not talk about that now. It will be explained in the requisition demo video. Instead, I will display this second window in the requisition part. As you can see in this requisition image, it was divided into 3 windows. In the upper windows are so-called new and future requisitions. Here you have an overview of what in this context is planned for the patient, perhaps months ahead, or perhaps minutes ahead, and virtually all data can be corrected. You can also move the requisition to another department so that the sampler goes to the department the patient may be currently moved to. In the moment the PTB is printed and the sampling process starts, the requisition line jumps to the middle of the window. In the middle window, requisition you cannot correct as the PTB has been printed and sampling may have started. But can you get hold of the sampler and perhaps manage to get an extra sample included on the same requisition? That is, no new PTB format used, and perhaps you can avoid having to stab the patient again, but simply use one of the extra spare barcode labels. The sampler which is taking the test can also request extra analysis, that is, make an update of the requisition at the same time as the sampler at the laboratory acknowledge the receipt of the sample tubes. At that moment, the sample material, the requisition line, jumps to the bottom of the window. Now the analysis process is underway. Here you can still correct the requisition, but now only on the Labka system itself, as mentioned in Chapter C. You can, for example, add analysis on the sample material you already have. In the image in the lower window or via search, you will be able to see all results as soon as they are available, as well as any remaining order. That is, results which will often come a little later. About the demo videos, I will recommend that you watch the first video with accumulated search and then the video with the two requisition procedures. The first requisition demo shows how you can, in a simple routine situation, order a group of analysis in just 1 minute, only 5 clicks. The second requisition video shows additional options. Here I will continue with a description of historical, commercial and technical conditions which were significant in the construction of the LSP. Thank you. Hi. I will tell you a little about the historical, commercial and technical conditions which were significant in the construction of the LSP. I would like first to mention that if you are wondering why it says CSC Data Lab on some pictures, while it says Advanced Data Lab APS on the interface unit between the HP 1000 and the front-end computer, this is due to the fact that in 1995 the majority shares in Dansk Data Lab was passed to the company Datacentralen AS, where the majority share was taken over by CSC in 1996. And that the development of the LSP had begun before 1994. Around 1990, a form of hospital billing system based on IBM mainframe and character-oriented screen terminals already existed in some hospitals in Denmark, our primary area. And several smaller local EHR systems were underway. But there were no LSP-like system with graphical interface in our area. Around this time, several hospitals had established LAN networks of different types. LAN networks such as Token Ring, ArcNet, Ethernet, network to which you had to adapt if necessary. In the following, I will briefly describe how the system LSC was built and then explain why and how the development took place. Let us look at the LSP structure. A. The LSP was based on the HP 1000 database image 2 and the work register in the file system on Labka on the HP 1000 with a total of 7 million, later 21 million patient analysis answers. B. Communication to the PC client in the clinical department via the front-end computer and IBM PS2. HP 1000 PS2 communication is handled via the HP 12006A parallel card on the HP 1000 and the duplex parallel port on PS2. C. Interconnection of the HP 1000 and the PS2 via the device CSI 101 high-speed computer server interface. D. On the PS2, the programming language was C. The operating system was OS2. DB2 was also used. E. The client based on Windows programming language C++. Around 1993, we had delivered several Labka systems with great success, and the success grew with the delivery of cumulative responses in 1989. So there were current and future hospitals we could deliver LSP to. We could base ourselves on the HP 1000 Labka system, where we have virtual or modules for storing the requisition information in blocks and retrieving requisition analysis response information with only a few physical disk scans. That is very short response time. On the personal side, individual Labka employees had, in addition to their IT training, laboratory technical training, as well as several years of work as laboratory technician and experience with work and blood sampling in the hospital's department, the interaction between the laboratory and the clinical department. A major reason for the flexibility built into the LSP. The younger talented Labka programmers on the HP 1000 wanted us to get more familiar with the new technique on the PC side, something other than just Fortran on the HP 1000. They chose the IBM PS2, DB2 and the programming language C. No, that was around 93. We lacked solid knowledge experience with object-oriented programming C++, but it came with the new people in 95. Particularly important for the project was that we did not have to add much load on the HP 1000 system, especially because it had to be assumed that the production would grow strongly, more than 5% per year. This could be done by putting load on the front-end computer and take advantage of the short response time on the Labka HP 1000 system. Also, by utilizing the HP 1000 and Image2 database and Labka programs, you could also completely avoid client license and thereby offer LSP at a very favorable price. Judge for yourself on this picture the number of LSP PC database clients around 40,000 and the number of users 38,000 in 2006. The focus was on register updating in Labka, especially on the search functions, as the number of searches around the peak period will be larger with several thousand PCs in the department. You can experience the ultra-short response time in the last part of the cumulated search in the demo video in the next demo video. About PTB. Designing the PTB an important and rather complex element in the lab system. Here we could use our own library for the laser printer control and experience from the cumulative response system, as well as the experience of the laboratory trained employees. Around 93, we assumed that we could develop and implement requisition and response system LSP on the existing and presumably future Labka system. We announced that in October 93 in the journal News About Labka. You may ask, why not communicate via network card from the HP 1000 to the front-end computer PS2? It was a problem on the HP 1000 to insert advanced driver net software into the actual HP 1000 RTEA core area, which was already well filled with software, drivers, many driver tables, ID segment, etc. Thus, the number of ID segments was, when the core area was filled, there was only room for 187 ID segments, tables that determine how many programs in the operating system can be handled at once, and we wanted no significant reduction of this number. We could instead use the driver for parallel cards, the HP12006A, which did not take much space. It didn't have many complex features, but it didn't need to. The HP12006A had a great transfer speed. It could even pack 16-bit words to 8-bit bytes via the hardware on the card. For the PS2, a driver port had to be developed, but no special software had to be developed on the HP1000 side. The result, among other things, this consideration was a structure as outlined earlier. I wish I could tell you something about the advanced software written in C on the front-end computer PS2, about the smart robust packet transport system, etc. The advanced client's Windows system in C++. Unfortunately, my insight is not sufficient for this. I would instead suggest watching the demo videos in English in the next videos. I have added a chapter on the interface unit CSI 101 high-speed computer server interface. It was developed in Dansk Data Lab. Only 25 were produced, so it is kind of a treasure that exists. It is probably here the only one which is left, in addition to the prototype you see here. It is not rocket science, but it was nevertheless important as it connected the HP1000 with thousands of client PCs in the clinical departments. But if you don't want a little simple peek into the hardware world, skip the next chapter in this video. Here, a small, easy, understandable, simple look into a simple hardware world. Here you see the CSI high-speed computer server interface. This is the prototype. It's here for historical reason. It wasn't not rocket science, but it was a pretty important little link in the chain. You can say that the task for the interface controller was to transfer data between the HP1000 and the PS2 with a transmission time that was reasonable, small compared to the other processes in the system. So let us take a look on the search and reading times with a personal registration number into the Labka HP1000 lab system. A cumulated page in the cumulative response system often consists of 10 blocks, that is 10 columns in average. As you can see here to the left, the disk read times for the entire page, that is 10 requisition with 100 results, will be approximately 500 milliseconds or 300 milliseconds depending on where data is stored in the registers. If you will see more detail about disk read time and Labka, see the guidelines in the end of this first chapter. I will continue here talking about transfer time and the CSI 101. Data is transferred in blocks. The transmission direction is often changed after each byte block that is transferred. A block of bytes will normally be from 32 bytes to approximately 4 kilobytes. For example, approximately 1 kilobyte for transfer of a block containing a requisition record with 10 result records, corresponding to a column in the cumulated response system. There will also be a small CPU overhead, but it is very small in that data is transferred as block internal in the HP1000 and read and written is via DMA, direct memory access. A simplified diagram of the CSE can be seen here. As you can see, there are separate 8 output lines and 8 separate input lines from the HP 12006A control board, while there are both 8-bit input-outputs alternately on the corresponding line from the PS2. In addition to the data lines, there are control lines for both sides to switch the direction of transmission and to ensure that the data is stable when the read and acknowledgement signals for data is received by the CSI. Electrical speaking, data transfer takes place via so-called CDL drivers and twisted lines. That is, that cable length from the CSI to the PS2 and the HP1000 must be only approximately 1 meter. I will do a little demo, so let's go to the HP1000 and make a little demo. Here you see the CSI 101 controller. And here you have the HP1000 Labka system, the computer, the disk, tape units and some terminals. If you want to get more information about the system, you should go to the information just after the first chapter in this video. But here we shall concentrate on the CSI 101 and communication. So let us take a closer look. Unfortunately, I don't have any IBM PS2 server here. Instead, I have connected the CSI 101 to the parallel card in the HP1000 CPU. And the cable, which is normally going to the parallel port in the PS2, is here connected this to a pulse generator, which simulates the PS2 parallel port by generating an acceptance pulse for each byte the PS2 receives. So let us go and look at the terminal. I will now start the test program for the parallel card in the HP1000. It is called PARTE. So I write PARTE, and you see in the menu here. I'll start with this function, the reset number 4. So let us go a little closer on. So move down here. I'll now select a multiple write at the doorway here. That means I can write buffers to the CSI, and that will normally go on further to the IBM PS2. I can decide what value do I want to put into that buffer. And the first word I will write as 0, and the next one I will write 255. Then I can decide how big should the buffer be. And I'll write minus 1100. That is approximately 1 kilobyte, and that is equivalent to 1 column information in the accumulated answering system. 1 requisition with around 10 results. Then I can select how many buffers, equivalent to how many columns do I want to send to the CSI, and I select 2000. And then I count to see how long time it takes, and you can also see that it's sending down here. Here it's 1 second, 2 seconds, 3 seconds, 4 seconds. It's around 4 seconds, and it was 2000 records. So that's about 2 milliseconds for each record. And if you remember, it took about 300 to 500 milliseconds to take out information from the file system for accumulated page. And here you can see for each column it takes 2 milliseconds. So that's only, the transmission time is only about 5% of the time it takes for pulling out the information from the file system. Therefore, we are calling it the high-speed interface controller. After this test, you may wonder, how much does it load the HP1000 to send this information? I will show you with a little test. So I start PARTE again. We do the same as before, but this time I will send 1100, but not 2000, but 25,000. So it will take some more time. And then I will go and look at the other terminal to the right here. So if you go over here and look, you can see up here PARTE is running, and it takes about 13% of the CPU time. It is still running. Why does it not load the computer so much? It is because, of course, its transmission is via the DMA, the Direct Memory Access Channel.